Starting the recording. Welcome everyone today to the We Are Neutral webinar called From Footprint to Fiction, the Murky World of Greenhouse Gas Calculations and Offsets, breaking down calculating carbon footprints, why it's important, and the science behind it all. At We Are Neutral, we are really, really passionate about ensuring that carbon footprints are comprehensive. All the protocols out there um, we follow, and then we add more layers to it to ensure that footprints are done correctly. Um, this webinar is also going to go over why this is all important, the science behind climate change, and then touch on offsets. Again, we're a pretty cynical group. We scrutinize the carbon offset world. We think that offsets can be done right, but there's a lot of ways that they're done wrong. So I would like to introduce Sam, my colleague, who is our calculation expert on the We Are Neutral team. Um, his bio is Sam graduated from the University of Florida in May in 2024 with a Bachelor of Science in Environmental Engineering. He's been with We Are Neutral for 3 years, and he specialized in quantifying greenhouse gas emissions, helping businesses understand and reduce their climate impacts. Um, Sam has been directly involved in assessing an environmental footprints of over 40 organizations, as well as utilizing frameworks such as the Greenhouse Gas Protocol to identify key areas for improvement and calculation methods. Sam is dedicated to advancing his expertise and has pursued continuing education with globally recognized institutions to deepen his knowledge and stay on the forefront of sustainability practices. So, super excited for Sam to lead us today. If you see at the bottom, there is a question and answer section. We will have 15 minutes at the end to answer all questions, and I will be monitoring that throughout the webinar. And now I will pass it over to Sam. Thank you, Sam.
Thank you, Anna, and thank you to everyone who came today. I'm really excited. This is my first webinar for We Are Neutral, so just going to get started. The first thing I want to do is provide a clear definition of what climate change actually is. So climate change is any long-term change in average weather patterns for a wide geographical area. Today, we're going to be mostly focusing on human-driven global climate change. But again, climate change is a broader definition. It means any long-term change in average weather patterns. In general, these changes are a result of imbalances in the Earth's energy budget. So the Earth is very unique among the planets that we know of in that it radiates almost exactly the same amount of energy out back into space that we receive from the sun. So it's a very delicate balance, which means really small changes in things like the atmosphere or the Earth's orbit can cause climate change and can cause that energy balance to be disrupted. What climate change isn't is climate change is not weather, although the ideas are obviously very closely related. So while yes, climate change can cause immediate local impacts and can worsen and intensify extreme weather phenomena, effects are generally best observed on a larger time scale with a wider lens. So if you have a cold front for a couple days, sure, maybe climate change affected that or worsened that cold front, but it's probably not the sole cause. Whereas if summer after summer, year over year, you're noticing higher temperatures where you live for multiple decades on end, that is really strong evidence that climate change is actually occurring and causing that impact. So what are the effects of climate change? You probably know the biggest one is rising global temperatures. So this is a chart that goes back 175 years and compares the temperature change to the average established between 1861 and 1890. So this goes back to right before the Industrial Revolution, and it shows the average temperature change. Obviously, all the way here in 2025, we're at 1.5 degrees Celsius, or about 3 degrees Fahrenheit, over those pre-industrial levels. And while that might not seem huge in isolation, keeping in mind that this 1.5 degrees Celsius is the average temperature for the entire surface of the globe, that is pretty significant. And if we zoom out a little bit and look at this same relationship over a larger time scale, This is the same data, except compared to a different average temperature for the past 12,000 years, which is give or take the same amount of time that humans have had civilization. And in this chart, it's not so drastic, the absolute magnitude of the temperature change we're currently experiencing, but you can see how drastic that rate of change is, comparing the difference between these natural cycles and gradual warming versus this spike in atmospheric temperature due to the effects from human activities. Climate change can also cause more frequent and intense climate disasters, and it does that by disrupting our jet stream and disrupting our weather systems. So our weather systems are very highly reliant on natural energy gradients, or changes of energy in the atmosphere. Then when you have a lot of greenhouse gases that are being produced that can trap heat and produce more energy, these energy gradients get disrupted, which makes the jet stream weaker. And since the jet stream kind of holds in all that cold Arctic air and keeps the polar vortex stable, when we have a weaker or unstable jet stream, all of that really cold polar vortex air can move south. That's what causes those really bad cold fronts in the winter in Canada and the northern United States. And it also allows warm air to move north, and those are the warming effects that causes things like melting ice caps and sea level rise. Aside from disrupting the jet stream, which can cause weather systems to stall, heat waves, cold spells, floods, the increased temperatures from climate change also cause more evaporation, which can dry out soils and plants, leading to droughts. And with less of that water in the ground and in plants, there's more moisture in the air, which can fuel stronger storms and heavier rainfall. With a warming planet, you will obviously get warming oceans as well. And as we know here in the southeastern United States, warmer oceans mean more intense hurricanes and more intense storms, and that's just not good for anyone. This chart shows the $27 billion weather and climate disasters in the United States. Those are just all natural disasters that caused at least $1 billion in damage. While, of course, economics concerns aren't our chief priority in the environmental space, this economic data is a really good proxy to determine how much damage is caused to things like ecosystems, to our infrastructure, how many people were displaced, things that we really do care about. But this just goes to show how often we do have these life-changing climate disasters, and climate change is only going to worsen these effects. So what drives climate change? The biggest thing is greenhouse gas concentrations. So this chart on the left is the same data from earlier, going back to pre-industrial times and measuring the temperature anomaly or the temperature change, except this time it's graphed alongside atmospheric carbon dioxide concentrations. This is what's on that right axis, the carbon dioxide concentration in the atmosphere in parts per million. And as you can see, between like 1900 and 1920 is when we really start seeing that consistent gradual warming effects. And the temperature change is pretty directly correlated with that carbon dioxide increase in the atmosphere. A lot of people are surprised just how closely these two ideas are linked. And it is a really good graphic to show just the causation of carbon dioxide emissions and atmospheric warming. But it's also important to note that carbon dioxide is not the only greenhouse gas we care about. This pie chart on the right side shows the total emissions generated from the United States in 2022. So carbon dioxide makes up around 4/5, 80% of that greenhouse gas inventory. Methane, chemical formula CH4, represents about a ninth or 11% of that impact. And nitrous oxide, which is one of the most potent greenhouse gases, represents around 6%. The remainder is made up of dozens, maybe even hundreds of other greenhouse gases. These are important. They do have an impact on the climate, and we do care about them. They're just emitted in far smaller quantities, and we're going to pay them less of a focus today, focusing on the three bigger ones. I'm going to quickly go over the major sources from human activities for each of these pollutants. So for carbon dioxide, The biggest ones is from fossil fuel combustion, and that is burning fossil fuels to produce energy at a power plant to supply it to municipalities. Non-energy use of fuels would be things like driving your car, maybe even using propane for a grill, anything else that uses fossil fuels, but not directly to produce energy at a power plant. Also, any industrial or manufacturing processes, especially with cement or iron and steel, are going to produce a lot of CO2, as well as any natural gas or fossil fuel production, manufacturing, distribution. All of that produces a lot of carbon emissions. For methane, agriculture is a bigger contributor to these next two ones, methane and nitrous oxide. Enteric fermentation is a fancy term for gases from the digestive system of ruminant animals and livestock like sheep and cows. And manure management, a couple lines below, is just the waste from these animals. Really big contributor to climate change. If you've ever heard the throwaway line that cow farts cause climate change, there is some truth to that. Additionally, any natural gas or petroleum product systems are going to produce a lot of methane emissions, as well as anything that is decaying or rotting in a low or no oxygen environment. Um, Things like organic waste decaying in landfills or wetlands and rice paddies. These will all have organic matter that's decaying underwater, which causes a lot of methane emissions. For nitrous oxide, again, agriculture is a big contributor. More specifically, the nitrogen fertilizer that's used on pretty much every farm across the country. Additionally, combustion is a huge source of nitrous oxide emissions, whether that's stationary combustion using fossil fuels for generating electricity or mobile combustion like driving your car. Additionally, anything with waste, human or animal, like wastewater treatment and manure management is going to create a lot of nitrous oxide emissions as well as certain industrial processes. So there's not going to be a quiz on all of this, and you don't have to memorize all of it. But this was just an exercise to show that greenhouse gas emissions don't just happen magically. They aren't just out there and we have no control over it. They're a result of conscious decisions, conscious actions, and demands made by corporations, consumers, and governments. These decisions are often made without a full understanding of their climate impact. And I think that's where a lot of the disconnect is. A lot of people want to do better, they just don't necessarily know how to. So the first steps towards improvement, towards reducing these emissions, is to have a framework where we can not only categorize these emissions, but quantify them in meaningful ways. This brings us to the three scopes. So these scopes are used in corporate sustainability, but they can be extended to any entity, including the individual. And these help to categorize carbon or greenhouse gas emissions into groups. So scope one is the most direct and the ones you're most responsible for. You have the most control over them. To scope three, which is the most indirect activities that you have kind of the least control over. So breaking down scope one emissions, these are direct sources of emissions. And by that, I mean you're physically causing that gas to be released in the atmosphere. You can imagine I have a big CO2 canister and I undo the nozzle and just let that carbon dioxide be released into the atmosphere. That would be an example of direct emissions since I'm physically causing that greenhouse gas to be released. Um, more often than a CO2 canister, you might have gas leaks from some of your equipment, or if you're a big facility that does chemical reactions to fabricate certain things, you might have emissions from those processes. But more commonly, on an individual residential level, this will be like fuels burned on site at your home, things like natural gas appliances like your water heater or maybe your oven. Scope one emissions can also include fuel burned for your personal vehicles or vehicles that you own. If you put gas in at the pump, unless you have an electric vehicle, your engine is going to be converting that gasoline to energy and to greenhouse gases. Scope two emissions are indirect emissions from purchased electricity. If you're like most Americans, you do purchase electricity from a utility company. and you don't really have a say in what fossil fuels or what renewable energy they use to supply energy to your house. I can't really go up to GRU and say, hey, I'd really appreciate it if you didn't use any coal energy to send to my house. The consumer doesn't really have any control over that, but again, it is still our individual electricity consumption, and we are still responsible for that. Scope 3 emissions include pretty much everything else you've done in your entire life that I haven't mentioned already for Scope 1 or for Scope 2. This includes things like commuting or business travel, if you're flying a train or taking a taxi or taking an Uber, any car or vehicle that isn't yours, those are Scope 3 emissions. If you go to the store and buy something, not only were there emissions associated in the manufacturing and the production of that product, but it also had to be transported to the store probably in a plane or a truck, and that's going to create emissions as well. Um, Also, once you're finished with that product and you throw it away, or maybe you throw away the packaging, that's going to go to the landfill. It doesn't get there magically. We have to send garbage trucks to, I'm sorry, excuse me 1 second. I'll be right back. There's someone at my door. Hey, I'm sorry, I'm working. I'm put it in the Yes, sir. Okay.
Please go stuck right here, and I gotta go one way or the other, you're talking in my path.
All right.
Bring the keys, I'll do it.
Yes, sir.
I'm sorry, buddy.
No, I appreciate you. I'm presenting something. Thank you so much. I'm sorry for that. I'm back. There are some people doing some work outside my apartment. Um, Anyway, so your waste goes to the landfill, and there are emissions associated with the decomposition and the transportation to the landfill from that waste. There are also some things called downstream activities. The best example I can give for this is imagine you are a vehicle manufacturer and you produce a truck. Obviously, there are going to be emissions associated with the manufacturing of that vehicle, but once you sell it, you can't just wash your hands of it and say that's all the emissions that this truck is going to be responsible for. That truck is going to be driven for maybe 100,000 miles. It's going to use fossil fuels during that time and produce a lot of emissions. Scope 3, once you get really deep into the weeds, it gets a little bit harder to quantify and to understand everything that goes into it. And it also gets harder to draw exactly whose responsibility it is for the production of those emissions. But it is still important to quantify and to measure because generally Scope 3 emissions is the biggest portion of our individual impact. Moving on to understanding how greenhouse gas emissions work, greenhouse gases have specific molecular structures that allow them to absorb radiation from the sun and re-emit it as heat. So it absorbs infrared radiation from the sun's rays, and the individual atoms kind of vibrate and move around, and this creates electromagnetic fields that interact with that energy and convert some of it to heat. And that heat is emitted in all different directions. So looking at the atmosphere as a whole, some of that heat is going to drift off out into space, and that's good for us because it doesn't warm our planet, but a lot of that heat gets directed back down into the Earth. And as these concentrations increase, more heat gets trapped in the Earth's climate system, causing a rise in temperatures. While all greenhouse gases do warm the climate through this mechanism, some are much more efficient at it than others are. So to simplify greenhouse gas reporting, greenhouse gases are often converted into a common unit called carbon equivalents, or CO2e. So as you can see here, 1 ton of methane is roughly equivalent to 28 metric tons of carbon dioxide. And what's a metric ton? It is equal to 1,000 kilograms. It's a unit of weight. And it is about, imagine a cube that has side lengths of 27 feet. 27 feet is about the height of a light post you might see driving down a road. So imagine a cube, the height, the width, and the depth of one of those light posts that filled up with a gas, whether it's methane, carbon dioxide, or nitrous oxide, will be about 1 metric ton of emissions. So this conversion to units of carbon dioxide is based on a metric called global warming potential, or GWP. This metric compares the radiative forcing caused by a greenhouse gas to that of carbon dioxide over a 20 or 100-year time frame. To define radiative forcing, it's essentially the amount of energy that an individual greenhouse gas will add to the atmosphere. So global warming potential compares the energy adding effect of a greenhouse gas like methane to the energy adding effect of carbon dioxide over the same time frame. So obviously, thank you. If you compare carbon dioxide to itself over a 20 or 100-year period, it's going to have a global warming potential of 1. Carbon dioxide is one of the weaker greenhouse gases. It is the most prevalent, and it is the basis which all other greenhouse gases are measured. Carbon dioxide lasts a really long time in the atmosphere. It can last anywhere from a couple hundred years to a couple 100,000 years. So it really likes to stick around. Methane is a much stronger greenhouse gas. Over a 20-year period, it has a global warming potential of between 81 and 83, which again, that means over a 20-year period, it adds roughly 82 times more energy to the atmosphere than carbon dioxide does. Over a 100-year time span, this drops from between 27 and 30. Methane lasts a really short time in terms of atmospheric terms in the air, only between 9 and 12 years for an individual molecule, but some can be expected to last a little bit longer than that. Nitrous oxide is the most potent greenhouse gas we're looking at today. Over a 20 or 100-year period, it has a global warming potential of 273, which again means 273 times more energy is introduced to the atmosphere if you have nitrogen emissions than carbon dioxide emissions. Nitrous oxide lasts around 100 years in the atmosphere, but again, some can last a little longer than that. These charts I'm going to show you are showing that radiative forcing effect, that added energy for a 1 part per billion increase in these greenhouse gas concentrations in the atmosphere. So just to go over what that means, let's say the atmospheric concentration of methane is 2,000 parts per billion, and with a snap of the fingers, we release enough methane to raise that concentration to 2001 parts per billion. This graph on the upper left side is showing the added energy in terms of watts per meter squared on the Earth's surface caused by that methane emissions. This upper right side is the same graph, but for nitrous oxide, and this bottom graph is the same graph, but for carbon dioxide. I want you to take 2 things away from these graphs. One, the more potent a greenhouse gas is, the larger the vertical scale of their axis will be. So nitrous oxide initially releases more energy than methane will, which releases more energy than carbon dioxide will, if you look at the scale of the graph. The second thing I want you to see is the scale of the horizontal axis. So this is the number of years after those emissions have been released. So after 75 years for methane, because it has a very short atmospheric lifetime, all of that methane that we originally released will be gone from the atmosphere. It also means that the warming effects associated with it will not be continuing because, again, there are no more methane molecules. For nitrous oxide, it will take around 500 years for all of these emissions to go away or be removed from the atmosphere. And again, carbon dioxide has a much longer atmospheric lifetime. It can last for a couple 100,000 years. So even after 2,000 years, we still have about a third of the individual warming effect that is still happening. The last thing I want you to understand about these graphs is that at any one point on this graph, it shows you how much warming is happening in that instance. When you look at the total area under the curve, that represents the total warming after however many years. So as you'll recall from before, global warming potential only looks at 20 years or 100-year timeframes. So let's take a look at what 20 years looks like. The shaded area is the total amount of cumulative energy added that's being taken into account by this global warming metric, global warming potential metric. And the unshaded portion is what's being ignored. So after 20 years, we can see that most of methane's energy adding effects are being accounted for. We only have a small section that's still white, not shaded, meaning that global warming potential is not including that. But it gets a lot worse for the other 2 greenhouse gases. Nitrous oxide, if you only take into account 20 years of energy, that leaves most of the actual impact that happens on a larger time scale out of the picture. And carbon dioxide is even worse. 20 years is just a tiny, tiny sliver, especially when you take into account that this line is going to extend for a couple 100,000 years before reaching zero. If we look at a 100-year timescale, maybe it's a bit better. It's hard to say. At least all of methane's energy adding effects are being accounted for. And with nitrous oxide, you're at least accounting for most of it. But then again, when you look at carbon dioxide, this is still a very small section of the total cumulative warming. While this kind of makes sense from a government and from a policy perspective, we can't really make policies that we know will make sense in 50,000, 100,000 years. This does not make sense from a climate perspective because we're essentially ignoring most of the impact that actually occurs from the introduction of these pollutants into the atmosphere. So what are some alternatives we can use? One is called global temperature change potential. And instead of graphing the actual energy added to the atmosphere, this focuses on the actual temperature change associated with that energy. This may seem like splitting hairs, but there actually is a difference. These two values aren't always directly correlated, even though they are related. And sometimes the temperature change can lag between 10 and 20 years after energy is actually introduced into our atmospheric system. But unfortunately, global temperature change still has the same main limitation as global warming potential, is that we have to artificially limit it and compare these molecules at a specific time horizon. And given the fact that we know they have very different atmospheric lifetimes, this just doesn't really make sense. The other two options we have are directly modeling these climate solutions and these pollutants themselves, or individually calculating and accounting for the greenhouse gases. Both of these options eliminate the issues with the misleading comparisons and the timescales, but they're a lot less accessible. They take a lot more work and a lot more expertise to fully account for. And in a perfect world, we could account for all of these greenhouse gases all of the time, but sometimes we just don't have the time or the money, or sometimes people don't have the expertise to use these alternatives. I want to go over some example greenhouse gas calculations. This is for scope one, so those direct emissions. Consumption data is essentially the data that describes your activities that we would get from you or from one of our clients. So if the activity would be driving, the consumption data would be the fuel you use, the gasoline that you use to drive. An emissions factor is what allows us to convert this consumption data to greenhouse gases. So we know that for every gallon of gasoline that's burned in a motor vehicle, 8.81 kilograms of carbon dioxide emissions are going to be released. So with these two data points, we have a really easy multiplication problem. 250 gallons times 8.81 kilograms per gallon gets us 2,203 kilograms or 2.203 tons of carbon dioxide equivalents. And again, because this has that equivalent tacked onto it, we're not just looking at carbon dioxide, we're looking at all of the major greenhouse gases. If you're like me, you don't know how much gas you've used in the past year. You might have a much better sense of the mileage you were driving. So let's take a truck that drove 12,500 miles at 7 miles per gallon. We have a different emissions factor because we're looking at diesel fuel instead of gasoline. Then we can divide the mileage by the fuel economy to once again get that consumption amount, 1,785 gallons, which we can multiply by an emissions factor to again get a nice precise number of emissions, around 18 tons of greenhouse gas emissions. Moving on to scope two, which is indirect emissions from purchased electricity. Let's say I live in Florida and I used 10,000 kilowatt hours of electricity last year. Depending on where you live in the country, you're going to be on a different electricity grid. And depending on which utility companies are adding energy to that grid for you to use, and whether they use a certain percentage of fossil fuels or a certain percentage of renewable energy, there's going to be a different emissions factor that's associated with it that's telling you how clean or dirty your energy is. For the Florida regional generation factor, we produce 381 grams of carbon dioxide equivalents per kilowatt hour that we use at our home. So again, this just turns into a simple multiplication problem and allows us to get a really precise value for the emissions that we're accountable for. If you live in an apartment, you might not know exactly how much electricity you use. You might just get the bill from the complex, which we can break down using electricity spin data, using the average price per kilowatt hour. And again, we're just dividing the total amount spinned by that 17 cents per kilowatt hour value. And now we have a consumption amount that we can use our emissions factor for to get 3.36 tons of carbon emissions. I have one more example for you. This is scope 3 emissions surrounding air travel or purchased air travel. So let's say you fly across the country, you've flown 3,500 miles. Depending on the length of your flight, you have a different emissions factor. This is a long haul flight. So for every passenger on that plane, for every mile that's flown, 163 grams of carbon dioxide are produced. And it's important to note that this is a per passenger metric. If you wanted to know the emissions from the entire plane, you'd have to multiply this factor by the amount of seats that are on the plane. So to calculate this, we just take the mileage, multiply that by the number of grams of carbon dioxide that are emitted per mile. And then for air travel, we add something called an aviation impact factor. This takes into account a couple of things. The first thing is that it's not just the plane fuel we're worried about. There are a bunch of support vehicles on the tarmac, and it takes energy to keep the airport air conditioned and with electricity. So all of these go into that aviation impact factor, as well as the fact as you are burning jet fuel at 30,000 feet in the air when you're cruising, and these emissions being released so high up into the atmosphere really exacerbate their effect compared to if they were released at ground level. So we use an aviation impact factor of 1.9. This can change depending on what's being accounted for, but we feel this is fair. And this gives a um, total emissions of 7.351 tons of greenhouse gas emissions. Let's say you are purchasing tickets for your coworkers, that's your role in your office, and you don't know the exact mileage or which airports these plane tickets are for. You just know the amount you spent. There's this really great data set from the EPA called spin-based emissions factor. And this basically tells us how much carbon emissions are associated with each dollar we spend for a bunch of different industries. This is the emissions factor for passenger air transportation, and this data is from 2022. So we have to convert the money that we spent on plane tickets. Let's say we spent that in 2024. We have to adjust for inflation first to convert this into 2022 dollars, which is the same year that this data was published. And then we get $3,125. We can multiply it by that spin-based emissions factor, tack on that 1.9 multiplier, the aviation impact factor, and again, get a precise number for that final emissions. So why does this matter? Why do we care about it? The main thing is that you can't reduce what you don't measure. You can incorporate all kinds of sustainable actions in your daily life, but unless you're measuring what was happening before and what was happening after and actually quantifying these emissions, you don't really understand the impact that those actions are having on the climate. Most people, this says most, this should say all, no one and no company are able to fully reduce your carbon emissions. Think of this on a personal level. You can be the most ecologically conscious person out there, but you still need to eat, you still need to go places. Even just living costs has a carbon cost associated with it. So it's impossible to reduce your carbon footprint to zero. This is true for companies and for people. The remaining impact has to be balanced out in another way if you want to not have an impact on the environment. And that brings us to carbon credits and carbon offset projects. So carbon credits are certificates that represent the reduction, removal, or avoidance of 1 metric ton of carbon dioxide or carbon dioxide equivalents. These credits are generated by carbon offset projects that are verified by independent standards. These projects can look like a bunch of different things. One thing that is really common among carbon offset projects, excuse me, is planting trees, as in reforestation. So as you plant a bunch of trees, these trees will grow, they'll absorb carbon dioxide from the atmosphere and sequester it in the tree's biomass. And this quantity of carbon dioxide can be precisely measured by measuring the tree and using a couple algorithms to determine how much of that biomass was from those carbon emissions. There are other options that include large-scale industrial processes that release a lot of methane and nitrous oxide emissions. Those emissions from these industrial processes can either be captured or they can be destroyed through incineration, and this significantly reduces the amount of emissions that are going up into the atmosphere. So carbon offset projects are essentially any measurable reduction of carbon emissions that can be packaged up into certificates. Um, what makes a good carbon credit? One of the big things is additionality, which essentially means that these reductions or these removals of carbon dioxide wouldn't have happened without this carbon offset project existing. So an example of this is, let's say you have a nonprofit that is restoring a forest out of the goodness of their own hearts. They just really like forests and want to improve the climate. You aren't allowed to essentially buy this land and tell these people to keep planting trees, except now you're going to turn it into a carbon offset project because that tree planting, that those carbon reductions were already happening. So you can't take credit for something that's already happening. Good carbon offset projects are also quantifiable and verifiable, which basically means they are following a methodology really closely and they are transparent enough to let people come and audit their project and check their work. Permanence essentially means that these carbon credits aren't going to be reversed in the future. And the best example I can give for that is also a forestry example. So imagine you're planting a bunch of trees in California where it's really dry, and then in the summer, a big wildfire happens and all of your trees burn down. Well, you've already issued a bunch of carbon credits, but the actual reduction, the sequestered carbon dioxide that is present in those trees, that is what your credits accounted for, that doesn't exist anymore. Those emissions are back in the atmosphere, and you've just issued thousands of carbon credits that essentially aren't making any impact on the climate. So permanence is a huge risk with some of these carbon offset projects. And the last thing that makes a good carbon credit are co-benefits. Co-benefits are any benefits, whether they're economic, environmental, social, aside from just the reductions in greenhouse gas emissions. So once again, using reforestation and as an example, you're planting a bunch of trees. Not only are you absorbing carbon dioxide from the atmosphere, but these trees are providing a habitat for millions of critters and organisms. It's creating cleaner air wherever you're planting these trees in general. And also you're creating a lot of jobs for the people who are managing these areas. So co-benefits are essentially every other benefit of a carbon offset project aside from those emission reductions. So where do some projects fall short? If all of the projects listed on these major registries have to be additional, permanent, and verifiable, why do we at We Are Neutral still think that over half of these credits aren't worth buying and are overstating their actual impact? Well, that's because even after following these methodologies, there are some common issues that can kind of fall through the cracks. One of these is that permanence risk. You can never fully account for natural disasters, but you can mitigate some of this risk of permanence for your carbon offset project by, let's say, planting trees in areas that aren't prone to wildfires or big landslides or anything like that. Permanence risk can never be fully mitigated, especially when you're doing carbon reductions, but they can be mitigated significantly. Baseline inflation is another issue where because you have to calculate the as-is scenario before your carbon offset project really starts to determine how much carbon emissions you are actually reducing. If you get those initial calculations of the as-is scenario wrong, you're going to inflate the amount that you're actually reducing in terms of greenhouse gases. Both permanence risks and baseline inflation can lead to the issue of overcrediting, which can also happen just by itself. Overcrediting is issuing more credits than you've actually produced at your project. This is obviously a bad thing because that means someone's carbon credits doesn't have the impact, the positive environmental impact that's associated with them. And that means they shouldn't have bought it in the first place if they aren't going to get any actual credit from it. The next big issue is project funding. Think of this as mainly a conflict of interest issue. You can understand how bad it would be if a carbon offset project were reforesting an area to sell carbon credits and to reduce carbon emissions, but they're also using a section of that forest to cut down trees and sell that for to the timber, to the lumber industry. It's just a massive conflict of interest. You have to wonder where their interests actually lie, if it's helping the client or if it's money or the climate or if it's money. We just don't want any outside sources of project funding besides the carbon credits itself. The other major issue is leakage. Leakage essentially means the carbon emissions that you're reducing are being undone, being re-emitted somewhere else. The best example I have for this, there are these carbon offset projects called avoided conversion projects. This is essentially there is a forest at risk of being cut down. Let's say a logging company wants to buy that land, and instead of the logging company buying that land, someone else buys that land and says, we're going to protect this land and make it so that it's never cut down. Well, this is great, but that didn't actually change anything. We went from having a forest that was sequestering carbon to still having a forest that's still sequestering carbon. Um, we don't really believe in the idea that because there is an imminent threat, that taking that threat away is an actual reduction in carbon emissions, especially since that initial logging company can just go 50 miles down the road and cut down trees somewhere else. So things like avoided conversion aren't always the best carbon offset projects because they're really prone to leakage. It's really hard to prove that not only am I protecting this land, but the threat to it won't actually happen anywhere else in the globe. That's kind of impossible to say with certainty. So the key points I want you to take away from today, climate change is already causing significant warming, extreme weather effects, and disruptions to our ecosystems, people, and society. Human-driven climate change is caused by greenhouse gases and the heat that they trap in the atmosphere. And while all greenhouse gases do work in this mechanism, their lifetimes and warming effects are very different, so we need to treat them differently. While global warming potentials are a useful metric, they really do oversimplify the physics of atmospheric warming effects. Greenhouse gas inventories and high quality data are really important, not only for just accountability and understanding your impact, but for making smarter decisions in the future that will lessen that impact. Carbon credits and carbon offset projects, they can and they do support climate action. They're a very necessary tool because, as we said before, we can't individually reduce our impact to zero. Still, many projects are overstating their actual impact and shouldn't be purchased due to these issues that fly under the radar. That is everything I have for you. I'm going to hand it over to Anna to tell us any questions that were sent in the chat.
We have no questions, Sam, which I don't believe is true. I'm sure people are just digesting all the information. Also, I think it's hilarious that your roof is being replaced during this webinar and you had to answer the door.
They
Um,
wanted me to move my car. I apologize for that.
That's amazing. Any last minute questions that our attendees have, you can put them in the Q&A box, and we can address them now. Otherwise, feel free to email us, sam@weareneutral.com or anna@weareneutral.com, and we're happy to address any questions that you may have. I just also wanted to take a second to say that I'm really proud of the work that We Are Neutral does. I'm really proud that we take into account um, so many things that was discussed today that other groups don't necessarily take into account. So we're really proud to be a comprehensive environmental, we call ourselves environmental mathematicians. And yeah, we're definitely here if any of you have a business or an organization um, that has questions. Winnie, I am going to allow you to talk. Let's see if this button works.
It does. Oh, hey, can you hear me?
Yeah.
Yes.
Okay, awesome. Thank you for the presentation, Sam. So you mentioned something about when you are doing the calculations for the aviation sector, aviation like part, You scope three, you mentioned the impact, I forget the name, something impact, the aviation factor impact, the aviation impact factor,
Yes.
which
Yes.
is the okay. So that and you mentioned that's just the additional like emissions that you know that are part of the operations for the plane to what to happen for you to ride the plane, like all the other things that come into it. And I wondered for vehicles as well. So when you're doing, say, transportation distribution for your company's products, does like there's things like the vehicle also has to like go to see a mechanic. You have to get it to a mechanic. You have to do all this other operational stuff to get it going. Is that factored in differently when you're doing the scope three for distribution of your goods and services?
So yes, we try to factor in as much as possible in terms of vehicle maintenance. We don't specifically calculate factor that in. We're more concerned about let's say like the distance being traveled and the actual vehicle being used. But you're absolutely right that there are additional impacts associated with that. There's just no really precise way to calculate that. The main reason for that is because all individual vehicles are very different. So like I might have, if we buy the same car, I might have a lot of problems with mine and the engine causing a lot of maintenance, whereas your car may not have those issues whatsoever. And with planes and air transportation, there's a lot less variance between those because all of these planes are getting a ton of maintenance. All of them require similar amounts of support services. So we don't automatically include that for vehicle travel the same way we do for air travel. And we rely more on our client telling us, hey, we had to get this maintenance done. That's why we asked about things like purchase goods and services. Maintenance would fall under that service. Um, does that answer your question?
Yes, it does. Thank you.
You're welcome.
Any other questions? This webinar has been recorded. We can email it to all of the attendees. And if you all have any questions after today, feel free to reach out. With that, I will conclude today's webinar. Thank you, Sam. Thank you so much, everyone, for attending. And we hope to see you at our future webinars. Have a beautiful Wednesday.
Thank you, everyone. Bye.